Faster constant V, positive. Slower,
But still moving in a positive direction.
yeah.
At a constant rate.
Constant V, also positive. Right there. The slowing down, you wouldn't even see the slowing down. This is not a curved thing. It's a sharp corner. It's fast, slower. Kenwar, good morning. If you could grow or shrink an animal to the size of a puppy to be your pet forever, what animal would you grow or shrink?
Dog.
Nice. So it's like a big dog, make him a smaller dog. Ahmad, good morning. If you could shrink any animal to the size of a puppy to be your pet, what animal would you grow or shrink?
Tiger for shrink.
A tiger? Nice. Okay, so it was fast, it's slower, and we know this because the slopes are different, and we know it's constant because those are straight lines. What's happening here? Zaid.
You're at a constant positive speed, and then you just stop moving.
Constant positive V here, and then you stop moving. Cool. What happened here? Connor again.
You start constant, moving in a positive direction, and it's kind of fast. Then suddenly the line goes much faster as it becomes more steep in a positive direction.
So this is faster. So it's positive, slower, positive, faster.
And then it stops, it plateaus as time.
Yeah, object stops moving.
And then it shoots back up again with a steep positive constant.
Careful. It almost was like you were describing the graph and not the object following the graph. And again, really picky, but the only thing I'm going to take exception to is that word up. We don't actually know which direction, we just know it's moving positively, but all of a sudden it starts to move with some positive constant V again. And you can talk about the different speeds here. Which section was faster? I'll go like this, A, B, C, D. Which one? They're all constant. Which one's the fastest? B, because it's the, and then C, because it's not moving in C. Cool. Does that help? Questions about C? Okay. Number 4, or number 3 rather. Number 4, same kind of deal. Beside the graph, describe the motion represented. If the speed is changing, state whether it's increasing or decreasing. What's happening here? Nice and easy one. Connor?
The line is beginning to move in a positive direction. Speed is increasing.
The speed is increasing, and it's positive. Cool. How about this one? Sorry, who said? I don't know who said anything. Zaid, you're suggesting it starts fast and then slows down?
Yeah.
Why would you suggest this?
Because it's plateauing, so then it's like moves less as time goes on.
Okay, so what you're looking at is steepness as you travel, right? So it starts really steep, and then it starts to flatten off, and once it gets totally flat, that means it's not moving. So it has to be going from a higher velocity to a lower velocity, and we know that velocity is what the whole time? Positive or negative? It's positive, because the graph is depicting this upward trend here. So it's slowing down, starts fast, slows down, but it's still positive V even though it is slowing down. This guy here is a little bit trickier. What's going on with him? Connor?
Line starts moving in a slow but positive direction.
Careful.
Speed is increasing.
Okay, so speed's slow, yeah, increasing.
Slowly increasing. And then it starts to get a little bit faster and then kind of tapers off a little bit.
What does that mean? Like, is it
the speed is decreasing and beginning to...
Okay, so it's slowing down.
It's starting to slow down and then becoming flat, which means it's stopping.
Okay. So it was speeding up, slowing down, stop. Cool. And at no point was it ever very fast, because it doesn't, nowhere along the line here does it look overly steep. But the fastest point is going to be, I guess, right here, right before it starts to slow down again. So that is 3 and 4. Jasmine, does that help? Okay. Then I said the photocopier cut the top line off. It says, it's supposed to say, beside each graph, describe the motion represented by each of the following displacement versus time graphs. So what's happening here? If an object does this, what has the object done? Give me the whole from beginning to end, Manuel. Connor.
Starts fast, stops, then it starts going down in the negative direction with the
But it's not going the line. Okay, careful. You jump back and forth between describing the object and describing the line. What's the object doing? The motion of the object.
going fast in a positive direction constantly, then going and stopping, and then it's going fast in the negative direction.
So what does that mean? Like practically speaking, it's returning back to where it came from. So this is a quick walk out, a stop, and a slower walk back. It's like when you go into the water fountain. You're dying of thirst, apparently, in class. So you huff it to the water fountain. You're at the water fountain for a bit, and then the walk back is noticeably slower than the walk out as you return to wherever you came from, perhaps class. This one, what's going on here?
You move in a positive direction constantly, then you move in a negative direction, like halfway from what you did before. When you move in a positive, same amount, negative in the same amount, positive in the same amount, and then negative in the same amount.
What situation could be described here? I feel like I've done this. This is me chasing my cat. Perhaps, right? Yeah. And then you got something like this. What's going on here? Okay. Yep. I gave you then this following graph. Don't worry about that writing on the side there. These were the values that I calculated for the average speed for each of the following time intervals and the average speed for the entire 22 seconds. Comments, questions, concerns about any of these values? We're cool with all of them? Okay, hearing nothing. Or are we still checking? Some of you are still looking. Okay. Then I didn't put answers. I added 3 questions. These ones down here, don't worry about this. That's a note for me for later. I wanted you to find the velocity at 1 second, 11 seconds, and 13 seconds. So those are instantaneous velocities because it's not a range of time. It's a specific time. I didn't give you answers here because I wanted to actually show you that procedure kind of right now. Just make sure that you were comfortable with it. So 1 second is here between 0 and 2. So I want the instantaneous velocity right there. So what I would do is I would go up here and I would put my pen there, and I'm going to draw a tangent line now for that point along the graph. So I've got my tangent line. I think it's okay tangent line. Maybe not. Tangent lines are hard to draw.
How do you know what angle to say you do that?
You're totally ballparking this thing. And then anywhere along the tangent line, it's whatever looks, it's like a line of best fit. Does it look good? And so you're going to need to practice. And the only thing that the only rule that a tangent line must follow that will help you a little bit more than a line of best fit is a tangent line can only touch at one spot. So if it cuts the curve around that space, like if I had done this line for my tangent line, that wouldn't have worked because it would have bled along the line a whole lot more. Like you want it to try and hit it at one spot. So it's actually, I'm going to use the second line here that I drew, and then you take the slope of it anywhere along that line, and the slope actually could look something like this. The slope here, it went over 4 and it went up 10. So it's a rise of 10 and a run of 4. Again, careful, don't count boxes because then you think the slope is 1. You actually have to use the scale. So I'm rising here from 20 to 30, and I'm running here from 8 to 12. So that's going to give me a slope of 10 over 4, which is 5 over 2, which is 2.5 meters per second. So that would be my velocity right at 1 second. Now let's do the next one. I wanted 11 seconds, so that's right here. So for the sake of this, I'm going to put my tangent line on the underside of the curve. And again, when I say we only want it to hit in one spot, that's locally. If I end up punching further down, that's okay. It's right here, though. I want it at one spot. And so I would do something like that, perhaps. Might actually give me a decent tangent. And so I punch through, I look at my grid. I don't have any really good spots. I'm going to use this spot here. Yeesh. I'll try and use that spot there. This one's not a great one. Sorry. So then my rise is 25. And my run is 8 to 22 is 14. Ew. So it's going to be 25 over 14, which is divide that doesn't go. What's 25 over 14? 1.79. Is we'll round that too. So that's my second one. And then the third one I gave you was 13 seconds. So that's going to be right there. So the tangent line for 13 seconds looks something like that, maybe? Because 13 seconds is right there. I may have been able to take it down a little bit. The other piece with the tangent lines is to get it to hit exactly at one point, what you want to try and get it to do is actually form a 90-degree angle with the curve. So the tangent lines, yeah, the tangent lines are hard to draw. I just want you to practice them. I'm going to use that point there, and I don't really have another nice point. I'll approximate that point there as being 7. So 7 to 14, that would give me 7 seconds. It's not a great graph for this, but that's okay. It's just about trying. And then this one is 15. So that's 15 over 7 is 15 over 7 is 2.14, yeah. These are all meters per second. So that's the procedure. If you got somewhere in that neighborhood, again, this is your first time doing something like this. If you got close-ish at all, that's all I want you to do here, is to play with these tangents. Because I know this is probably the first time a lot of you have ever looked at doing something like having what a tangent line even is, never mind using it for something. So I wanted you just to try with those 3. You guys are going to do, I'm going to care a lot more on the lab about how we do these things, but the graph is actually going to be a lot bigger. It's going to be a lot easier to deal with, and it's going to be your own data that you're going to find tangent lines of after you draw me the curved line. So that's coming probably Tuesday or Wednesday next week, because we don't have Monday. But you can do another lab for me next week. Sorry? Early next week, Tuesday or Wednesday. Questions about that procedure? Hands up if you tried it. You're like, yeah, I tried the tangent line thing. It was kind of a mess. Okay, not nearly enough of you. Did we do the homework I assigned? Some of us did. Fantastic. We just didn't do the tangent line stuff. Okay.
Where can I find like the recording for the classes?
The recordings for the classes are, I will show you again. If you open the Google Classroom, this is going to be very slow because I'm currently I'm actually recording this. If you go into the Google Classroom, I'll put it on here. Bam. This is Physics 11. And we are in the classwork tab where it says course info. It says here class videos. You click on class videos. This is a link. I don't know why the image is screwy, but this, if you follow this link, it'll take you to another tab. I don't know if I have enough tabs open. Oh, actually, I need Reddit. Someone's trying to do a Dance Revolution thing, and so we're trying to figure out how to use it. So I actually need to have the Reddit thing open. But it'll bring you to this playlist here. It's Physics 11 Spring 2022. That's you guys. And it should be in order of the date I post it. If it's not, I think you guys can sort it. It's up here at the top, but they're all in order by date. And so there it is. This is yesterday's video. There it is. Bam. Okay, the other thing I gave you is I gave you some additional questions back from this worksheet here. These were the, I gave you these first three. So I got 720 seconds, 26.74 kilometers per second, and 2,116 meters. Sorry? Yes. Yeah, I converted 303 days into seconds because it wanted the answer in kilometers per second. And I'm wondering if I screwed up that last question. 900 times 24, number 3. Yeah, no, that's the same thing. Okay. Questions, comments, concerns on any of these three? Going once, twice. We're cool with these ones, okay? I hope. Okay, graphing, calculate the velocity of the automobile. These were the values that I got. 2, 0, negative 2.5, 0, 4.4. Question 7. I did not put on graph paper, and so my scale is all sorts of gross. No in advance. This is not a nice looking graph. And to really make it usable, I would have had to actually have to put this thing on graph paper. But you want a graph that looks like that. You've got the key piece here being the Sam getting a head start piece means his position starts at the 30, not at the 0. And then you've got speeds here. Harry's going at 10 meters per second, having started at 0. So that's a rise over a run. That's telling you in 1 second he went 10 meters. And so I just went in 10 seconds he went 100 meters. That's the slope there. Sam's slope is a lot less steep. This is not where the intersection is supposed to be. This is where my scale got all sorts of screwy. The intersection is actually supposed to be further along the way here. And if you had actually done this on graph paper, you would have seen this properly. But you're actually able to do it without reading it off. We could read it off the graph, but the other piece to it is we can do the algebra here. So does Harry win? If so, at what time? Yes, Harry won because at the 10-second mark he gets to the end of the race, and Sam is only at he should have been up here at 90 because 10 seconds in he went 60, but he started at 30. So I actually screwed up my graph. He should have been here. That's what that's where my mistake is. Bam. That is what the graph should have looked like. That's Sam. So I actually screwed up my graph. Because Sam went, and here's where I screwed up. Sam went 60 meters in those 10 seconds, but he started at 30. So I should have gone from 30 to 90 instead of 30 to 60 was my mistake. So you want a graph that looks something like that. And so if we want Sam to win, this whole graph just needs to slide up 10 meters. So then Sam would have to start anywhere above the 40 meter mark is the head start that Sam would need to win. And then they cross at the 7.5 second mark, which actually looks a lot better here. So something that looks like that. How do we do with this graph? Comments, questions, concerns on this? Okay. And number 8 is particularly challenging if you've never seen something like this before, but if you were in my Math 9 class, we did a whole unit on questions like this. You've got someone going from Hamilton to Toronto and Toronto to Hamilton. It's just using D equals VT, but what it's doing here is you know the total distance is 50. You don't know how far the Hamilton train goes. You don't know how far the Toronto train goes. So I called the Hamilton train D. I called the Toronto train the entire distance minus the distance the Hamilton train went, and we know they start at the exact same time. So I've got two equations. Because T equals D over V, I can set those two times equal. So D over V equal for Hamilton equals D over V for Toronto. This is my Hamilton, this is Toronto. I solve it for the displacement. I got 20 kilometers in, and then I plug that back into my equation right here, and I got 24 minutes. So it's the same kind of stuff that I've given you, it's just now you have to set it up like a system of equations. This is the kind of word problem that I gave my pre-diploma Math 9s, which means you should have, depending on who your math teacher is, I'm really hoping you saw stuff like this in grade 10. You should have seen stuff like that in grade 10 if you didn't. But question number 8, that's the curveball. Questions on any of this? We're feeling okay with this stuff? Kind of, sort of? If you guys don't ask questions, I can't help you, and I have no idea then how much you've done. So the only way to find out is to actually, see what you can do. So if there are no questions, comments, or concerns, I want you to close your books. Let's see how we did. This one's really short. It's one graph, and you're analyzing the graph. It's really no. You don't need a ruler. You don't need a ruler. It's all given to you. This thing should not take you more than like 5 minutes. It's just reading graphs. Can you do it? Nice and easy. On your mark and set camera when you got it. Here you go. If you want a calculator, you can use a calculator with everything else here. I feel like this is super straightforward. Oh, dang, it shrunk the thing. We done?
No.
No. Okay.
This is C. This is D. Does it actually matter what you know? Because of these. Correct. Never erase the word. You just keep asking if it's actually not correct. I don't know how you show me what. Yes, sir.
I have to double check one of my calculations. Hands up if you still need some time. Okay. I want to save the next drawing for one that will actually give you some time to do it because I don't think there's going to be a lot of time. There shouldn't be a lot of time to, much time left.
not move fast, right?
No.
Okay, here we go. So we've done velocity, we've done displacement, we've dealt with time. We've danced around the ideas of what happens when things speed up or slow down. So let's actually deal with it properly now.
Everyone is left in the road.
The only one who's left there was Angelina.
Really?
Well, Indu's sick, Angelina's sick, and Austin's dropped, so you're missing 3 or 4. That's okay. No, we must do work. We must always do work.
Is it Thursday today?
Moving forward, yes, it's the last day of the week.
Really?
Hey! We're gonna party.
Tomorrow's gonna be a good day, bro.
That won't be like you have to
Okay, here we go.
Wait, Mr. Rudolph, did you put a copy online?
I did not.
Okay.
I'm hoping to get ahead to help you out tomorrow, but everything right now is not scanned. I don't have a PDF of these things. Okay, here we go. Bam, let's do this. So,
I suggest you write down the stuff, or you can actually rewatch it.
don't memorize everything. Actually write some stuff down.
You got it.
Here we go. So, acceleration, let's talk about it. So, you're sitting at a stoplight, and the driver hits the gas. What do you feel? Okay, hands up. Hands up. What do you feel? Brendan, what do you mean? Can you explain?
I'll use aircraft example. So when fighter jets like sit in turn or really aggressive turns,
Yeah.
the G-force is that times your body weight pushed against you. Say they have 12 G-forces pushed on you, that's 12 times your body weight being pushed onto them.
Where is it? What do you mean being pushed onto them? Like, where is it pushing?
It's pushing all across the body. Like it's force being pushed on you from the momentum.
Okay. Okay, so there's, I mean, if you're sitting at a stoplight, you're not, unless you got a crazy car, you're not feeling a lot of G's, but you might feel that same kind of pressure. Manuel?
I feel like the car wants to move, but my head like stays still.
The car wants to move, but your head stays still.
Yeah, like,
What do you mean?
Like the car moves for like ran for like a slight second, like I like stayed in the spot and then the car.
Okay, so let's write this down. Connor?
Well, the car is moving, but you're not moving yet, and that's when you're in the car, and sometimes you can go a little bit faster, and you don't necessarily feel it because you're moving at the same speed the car is. You can't feel the difference because your two motions are combined, but when you're taking off, the car is the thing moving before you're actually moving. So that's why you do that.
Okay. So let's write down a few of what yes, Khalil? So the car jerks forward and you jerk.
Or you stay in place, but the car is going forward.
But the car is moving around you.
Yeah, the car
Okay.
is
I like that I'm hearing that. That's not often the answer that I'm getting, that I get. Often the answer that I get is this idea of you guys being pushed back into your seat, which is kind of what Brendan suggested, but you danced close enough to kind of the actual physics. Newton. That's the buzzword in physics, right? You danced close enough that you didn't quite say that, So let's write down some of what you guys said. So you guys said G's. That was Brendan's thought. The idea that he extrapolated this, and you're not sitting at a stoplight anymore. Now you're in a jet, and the jet's accelerating, and you feel the weight of, it feels like your weight's increasing. But what's actually happening is a combination of what Khalil and Connor said. The idea that you are stationary in this particular example. And the car pushes forward around you. Often students will say, well, I feel like I'm being pushed backwards. Well, being pushed backwards in a car that's not moving is going to feel exactly the same as if you're not moving and the car is pushing forward around you. Functionally, it's exactly the same thing. Your perspective is different in those cases, but functionally those are the same thing. Or conversely, imagine you're driving at 50 kilometers an hour when the driver slams on the brakes. What do you feel? Sorry? Negative G's. What does that mean? The car stops, but your body wants to keep going. Inertia. That's another buzzword in physics. Where have you heard of inertia?
Driving test.
Okay, what is inertia? But what?
When you're going forward at a high speed, for example, and all of a sudden you try and take a turn, but it's too fast, your speed, your momentum that's propelling you forward, overrides the grip you have with the ground and keeps you going forward. I think something like that.
Okay, Tristan. Oh, sorry, one sec, Louis. Tristan, and then you.
Like, it doesn't matter what speed you're going. Like, if you just take a turn normally, you kind of feel being pulled to the opposite direction because your body wants to keep moving forward. Right?
Okay, Louis.
It's kind of like what you can see when you break the inertia. When you break the inertia, is the moment that you start moving. I think that is it.
Okay.
Like to break the inertia of the steer, I need to.
Oh, that's friction. I think is what you're describing, breaking friction.
No, it's friction. I think the inertia increases this part too.
Okay. Okay. Maybe then I'm not totally understanding what you mean, but I'll explain in a second. Tell me if that's what you meant. Khalil.
Inertia is basically say you're coming off the highway and you're doing like 100 or 170 and you're going to
Those are very different speeds.
take a loop around and you're trying to turn, but you feel pressure going on to the left side of the car. That's the car trying to still go forward while you're turning.
Is that what's happening? Is the car still interesting? The physical, how you're perceiving it. I'll give a couple more, and then I'll explain inertia. And I'll give you the definition of inertia and how it relates to everything that you're describing here in a sec. Manuel. And then James. Say that again.
Objects in motion once they stay in motion, and objects that are still once
Did you just
continue being still.
Did you just look that up?
That was trying to
You're
That's what you were trying to say?
have focus
like that.
Okay, so, and it's not just in motion, but in exactly the same kind of motion that they're in. So the example that Khalil gave, with you're fast, you're in a car, you turn the wheel to the right perhaps to follow that loop, and you feel like your body, like you feel like you're getting thrown to the left side. What's actually happening is your body wants to maintain the path that your body was in. Your body was going straight, and now you're telling the car, now it's time to go right. So the car is going to follow that path, but it has to drag your body with it. And there's a few different ways that is going to happen. A combination of the seatbelt and the seat around you. That's why a high-performance car has those kind of deeper seats, because the entire seat is basically cushioning you and dragging you around the corner. If you were trying to drive a Lamborghini, for example, and the front seat of a Lamborghini was like a van bench, yeah, you'd be sliding all over that thing because it's not, at no point is it actually trying to guide you anywhere. But if you ever sat in a luxury car, I've never sat in a Lamborghini, but I used to go to the car show. I love the Porsches, and I would sit in those and dream. The whole area of those kind of luxury cars, the front, I don't want to call it a cockpit because it's not a cockpit, but that's what it feels like. It feels like you're completely contained by the seat, by the seat belt, by the steering wheel, because to be able to stay with the car needs to drag you around. The car is going to do what you tell it to do, but your body wants to remain in the motion that you have. And if you don't have anything stopping you or guiding you around, you're going to keep going. So if you're driving at 50 kilometers per hour and the driver slams on the brakes, often what I'll have students describe is this idea of being flung forward. They were just sitting normally, and now all of a sudden they're just going. But that's exactly backwards what's really happening. The car is slowing down. Their body's just doing what their body was doing the entire time. It feels like now they've been pushed, but they were being pushed the whole time. This is what it feels like when the push suddenly stops. So imagine you're driving. What do you feel? What you feel is, versus what's actually happening. How do I even say that? No. Well, and this, you say dumb people. It's not always dumb people. Sometimes it's just misguided people. My sister-in-law was thrown through when she was a child. She was sleeping in the back seat, and it was a snowstorm, and so they thought slow enough. This would have been my mother-in-law. She thought she was going slow enough and went off the highway and down an embankment. And the car wasn't going forward very fast, but it rolled when it went down the embankment and launched my sister-in-law's body kept going the direction it wanted to go as the vehicle moved around her, and she was thrown out of the vehicle. She's not stupid, but perhaps mother could have told her to put the seatbelt on. The thing you're feeling here, the pushing around you forward or the pulling back, of the seatbelt, perhaps. This is the feeling of acceleration. Acceleration is the push that you feel when your velocity changes. The ideas of inertia are going to come in when we talk about Newton's laws a little bit more when we hit forces. But it's actually, you mentioned it, so it's not a bad place to start talking about it. Objects in motion want to remain in motion. And so to cause them to accelerate, either positively or negatively, you have to do something to them. When you do something, you're going to change the velocity. How quickly you change that velocity is going to be how we define our acceleration here. So we'll give it a few different kinds of definitions. First, verbally, accelerate, or with words, acceleration is the rate of change of velocity. So, just if that set of words doesn't make sense, it's how quickly velocity changes. So if you had to demonstrate this thing mathematically, if you had to relate acceleration and how quickly velocity is changing, what equation might do that? Yeah. A equals you're combining units and variables, and you're combining more than should be combined.
Okay.
Connor.
I don't know exactly what equation, but if you had it on a graph,
No, hold on. Hold that thought. We'll talk about graphs in a sec. Let's look at this line right here. The rate of change of velocity. So we want to know how quickly our velocity is changing. So that's going to involve a few things. When I talk about how quickly something's happening, what variable am I looking at? I'm looking at time. When I'm talking about how quickly something's changing, what I'm using to measure that is time. Did it happen in 5 seconds? Did it happen in 10 seconds? The shorter the time, the quicker it's happening. So there needs to be some involvement of time when we're talking about the rate of change of something. And in this case, we're talking about the change of velocity. So how could I write that using notation that we've already seen? Do I want positions? What you're describing is velocity. We had rate of change of position when we're talking about velocity. So you had a change in position was a position final minus a position initial, and we divided that by time. Right? That's how we figured out how fast you were going. Yes? That was velocity. One of you is nodding. Thank you, Nia. Now we want the rate of change of velocity. So it's the velocity now that's changing. So how do I write that mathematically? Well, I'm going to call it VF minus VI, sure. So that's the velocity that you are at the end minus the velocity you started with. And to figure out how quickly that's changing, what do I have to divide it by? Yeah, time. It doesn't have to necessarily be seconds, Manuel, but typically it's going to be seconds. This is not often how students give it to me to start. You jumped straight to it, Manuel, and that's great. Often when we talk about these things, when we're talking about the change of something, there's a mathematical notation I gave you for the change in something. Delta. So typically acceleration can also be thought of like this, a change in a velocity over time. So delta V over T. I've already drawn it with the arrow above it, but because velocity is a vector and acceleration depends on velocity, acceleration is also a vector. Means you need what when we talk about accelerations? You need directions. Directions matter when you're talking about acceleration. And Manuel, you already said it too. If I'm talking about units, a change in a velocity has what units? Or velocity, let's say it this way. Velocity has what kind of units? Sorry? Units. Like what do we measure a velocity in? Meters per second. Or kilometers per hour. So our change in our velocity is also going to be measured in meters per second or our kilometers per hour. But I'm also now then dividing that thing by time. So I'm going to have a meter per second divided by seconds, or I'm going to have a kilometer per hour divided by hours. When I have a meter divided by seconds and then that thing also divided by seconds, I can rewrite this thing as it being a meter per second squared or a kilometer per hour squared. This is the set of units that we use. I have never seen kilometers per hour squared because those numbers get ridiculous and really hard to actually wrap our brain around. Meter per second squared is typically the units that we use to describe acceleration. So what does it mean for an object to accelerate at 2 meters per second squared? What does that mean like in the physical world? Yeah.
So the object is moving 2 meters 1 second.
Okay, so we've got a meter per second squared. I'm going to write out 2 different ways that people actually read this using words, and that might help us here. So this is either a meter per second squared, or, oops, sorry, sometimes people will actually quote it like this and say it a meter per second per second. Okay? And sometimes I think reading it like this as a meter per second actually helps us with the understanding of what we're talking about here. So if I have a, and I'll try to emphasize it for you a particular way. If I have a meter per second, what does that mean? Connie, you want to try again?
To me it sounds like you have a meter per second and then another second,
Kind of. You're stacking them. So a meter per second is our velocity, the second is our time. So if I'm accelerating at 2 meters per second, does it help at all, Connor?
I think I might be onto it. So it would almost be like your next second increases or something, like your speed increases through the next second.
There it is. Every second, your speed, or in this case, velocity, increases by 2 meters per second. So, assuming that we're not moving at the beginning, if I tell you that we're accelerating at 2 meters per second, how fast are we going after 1 second? 2 meters per second. At 2 seconds, how fast are we going now? We increased by 2 meters per second. And now this second, we're going to increase by 2 meters per second. Now we're going 4 meters per second. Now we're going to increase by 2 meters per second again. So now I'm going 6 meters per second. That's what a 2 meter per second squared acceleration actually means. Cool? We can talk about acceleration and it kind of makes sense, but now as soon as we start adding numbers and units to it, this is where students typically start to get uncomfortable. Because you've all experienced accelerations before, but now I'm actually making you talk about it in the context of math and numbers, and that's where students seem to get concerned. Flip the page. The rules for the direction for the acceleration are the same as they were for velocity and displacement. Okay? But what they mean practically is a little bit different. So, for example, let's say I have an object. Here's my object. For all of these, all 4 of these pictures, we're going to say that this direction is positive. Okay? So if I have this object, and it has a velocity in this direction, what does that mean? What is, if I tell you that if my block has a v to the right, what does that mean, practically? It's moving to the right. Okay? What if I also tell you that it's accelerating that way? It has a velocity to the right and an acceleration to the right. What does that mean? Connor?
The velocity is like the speed in the direction that you're going, and then the acceleration is how much it's increasing by.
So what's actually happening to my block here?
It's increasing in speed, you get a curved line. Like that.
On what kind of graph?
Distance time.
That's true. But what does it mean for my object here?
It means it's increasing speed.
So it's accelerating. It's going faster. It's speeding up. Sweet. Love it. So velocity, we can say velocity is increasing and positive. If it's increasing and positive, this thing we could say in kind of more common language, this thing is speeding up. Cool. What if I have this? Let's use a different color. We'll go to red. I got my block again. I've got a velocity this way, and I've got an acceleration this way. What does that mean? Manuel. Okay, so velocity is still positive, but because my acceleration is backwards, that means my velocity must be decreasing. So as Manuel already said, in kind of common vernacular, we would say that this thing is slowing down. Zaid has a thought. Zaid, what's your thought?
Doesn't it say a negative acceleration does not mean you're slowing down?
We're not done yet. It doesn't mean you're slowing down. In this context, in this example, it does. In another example, it might not. Which is actually the next one. So Zaid, if you had waited 15 more seconds. What happens if I have this block? I tell you that I have a block with a velocity that way and an acceleration that way. In this case, both my velocity and acceleration are what? Which means they are negative. But because they're in the same direction, my velocity is getting faster. It's getting larger negatively. It's getting more and more and more negative, which means this thing's going faster and faster and faster in a negative direction. So I've got a negative acceleration here. This implies my acceleration is negative. My velocity is negative. I shouldn't have put the A there. I should have put just the negative. But when they're both negative, it means the acceleration and the velocity are acting in the same direction.
Velocity acceleration are increasing, but there's an opposite direction.
Sorry, one sec. I heard the first part you said. So it's increasing negatively. Luis, what was the second half of what you said?
It's just increasing acceleration and velocity just in another way. So
Yeah. So the first one we said the velocity was increasing and positive. Now it's increasing negatively. So what's actually happening here? It's speeding up. Going the other way. So in this one here too, I had an acceleration that was negative. In this case, the negative acceleration meant slowing down. In this case, the negative acceleration means I'm speeding up because of how it relates to the existing velocity. If acceleration and velocity are opposing each other, you're always slowing down. If acceleration and velocity are pointing in the same direction, you're always speeding up. The positive and negative just tells you which way. So then the last combination of things that we could include here is going to be what happens when I've got my object that has a, oh shoot, I need red again, it has a velocity this way and an acceleration this way. In this last example, my velocity is negative, but my acceleration is positive. So what's actually happening here? Velocity is decreasing. You said it already, negatively, or decreasing in the negative direction is how I'll say it. This should be blue. Dang it. So what's happening here, you said, the guys at the front said it already, it's slowing down while moving negatively. Comments, questions, concerns? We cool with this? Someone respond.
Yeah.
Okay, I know it's first block on a Thursday morning, which is actually a Friday morning, but we're good. Okay. So there are 4 formulas that all deal with acceleration in kinematics. If you look at the back of your formula sheet, if you don't have it out, I'll show you it here. The formulas that we're going to deal with are these ones here. This one, this one, this one, and this one. I can show you where they all come from if you want to see it, but I don't. You want to see some of them? Okay. First one is this guy here. So I'll start with our original definition. We said acceleration was a final velocity minus your initial velocity divided by how long it took you to make that change, right? This is the definition for acceleration. A equals v final minus v initial over t. What happens if I solve this thing for vf? If I solve this thing for vf, the first thing I want to move over is that t. So I'm going to multiply by t, I'm going to multiply by t. It's going to cancel on this side. And then I'm going to add vi to both sides. I'm going to be left with a vf, and that's going to give me a vi plus my a times t. That's that equation right there. Oh, we are running out of time, and these last ones are a little bit more involved. I will show you the. I do want to do a couple examples with these? And I'll do them on Monday, Tuesday. I want to show you the use of this question, of this particular formula here. So let's do a single example. You're not. Oh man, this is so sad. You're not going to have any homework over the long weekend. A moped traveling at 18 kilometers per hour accelerates at a 1.5 meter per second squared acceleration for 6.4 seconds. What is the final velocity in kilometers per hour? So the procedure is exactly the same for what we've done before. We have, and I want to see you do it. So write out what we know. We know that initially, how fast was our moped traveling? Going 18 kilometers per hour. We know that it was given an acceleration of 1.5 meters per second squared. The time it took to do that was 6.4 seconds. And we want to know what the final velocity is in kilometers per hour. So that's what we're looking for. So given the data that we've got, what you want to do is you want to isolate the appropriate equation given what you have and what you're looking for. So the reason that I did the one, and now I'm stopping to do this first question is here, because I'm given VI, AT, and VF, I want the equation that involves VI, AT, and VF, which is this first one here. V final equals V initial plus acceleration times time. So I'm going to write out my equation, VF equals VI plus AT, and now I'm going to fill the thing in. I know that my initial velocity was 18 kilometers per hour. I've got accelerations in meters per second squared and times in 6.4 seconds. So maybe I'm jumping the gun here a little bit. I want units that are consistent. So what's easier, kilometers per hour into meters per second, or these ones getting transferred over to kilometers per hour squared and hours? This thing going to meters per second would be nice. But we can make that conversion at the end. So let's do that. Forget what I was about to write. What's 18 kilometers per hour in? Sorry? 5? It's divided by 3. It's exactly 5? You did that? Okay, cool. That's what I got. We divided by 3.6 to get 5 meters per second. So now rather than, shoving in units that don't make sense, now we've got a consistent set of units. I've got 5 meters per second plus, and when you guys do it, you don't have to necessarily put the units here, but I want to show you what the units are going to do. I've got 5 meters per second times, or plus rather, 1.5 meters per second squared times 6.4 seconds. I'm multiplying seconds and meter per second squared, so this second here is going to cancel with one of my 2 seconds on the bottom, right? Because I've got seconds squared. So that's seconds times seconds. That seconds is going to cancel with one of those seconds squared. So this is going to give me 5 meters per second. I'm doing this in way more detail than perhaps you guys need to. 1.5 times 6.4 is 9.6. And now I'm left with meters per second. 9.6 plus 5 is 14.6 meters per second. So you guys are going to typically shove this thing into your calculator. You're going to go straight from here to here. But I said I wanted my final answer. The question is I want my final answer in kilometers per hour. Which means I need to multiply it by 3.6 to give us what? 52.56 kilometers per hour. Cool. So that's the procedure. I'm not going to give you any homework over the weekend. I'm going to show you these derivations on Monday. And then we're going to finish this up, or Tuesday rather, and Tuesday will be a work block for you here. When the bell goes, you may also go. Naya, just head. I'll call the office and sign you up. Hey Joanne, this is Steven. Calling to sign out Naya. Thank you. Okay. James, you handed in your quiz, yeah? James, you put your quiz in the bin, right? Okay, cool.